Good morning, sir. My name is Timothy Thomas George, registration number 20 BCE 1278. The topic of my video lecture is how Bitcoin achieves decentralization. And uh, in this presentation, we are going to talk about centralization versus decentralization, how these two concepts compete with each other, and we'll be talking about consensus, how consensus is obtained in distributed system, and then we'll particularly go to how consensus is obtained in blockchain. And finally, we'll also look at some of the applications of this, especially in preventing malicious nodes and preventing double spending attacks in Bitcoin. First is centralization versus decentralization. So centralization and decentralization are two paradigms, two computer science concepts that compete with each other, and this is something that's not only limited to Bitcoin, it's also in many other technologies. We'll find software services that could either be centralized or decentralized. We find even in real life, for example college classes, they are they centralized? Do we make them decentralized? How much of a decentralization power do you want to give? So these are concepts that extend way beyond Bitcoin and beyond computer science. And something that I we need to clear is that decentralization is not all or nothing. Many people have the idea that decentralization means that there's complete power to the individual to individuals, and there's no higher authority that has any power. And this may not be the case. There are many, in most practical scenarios, there's a certain level of power that's given to decentralized, to the lower lower in command, and there's a certain amount of power given to higher command. And if there's more power given to things lower in the hierarchy, it's more decentralized. And so decentralization does not mean to completely get rid of the central authority. And here is an example that we see here. That's email. In email, so email is a decentralized process. When we send an email to someone, we have the SNTP protocol that sends from one node to another node, and this is completely dependent on those two computers only. But if you see today practically, there are few mail services that dominate the entire email space. For example, you have Gmail, Yahoo Mail. These 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 are certain webmail services that completely dominate the whole today's internet emailing domain. And so, though the basic structure is decentralized, there's still a central authority that's providing this service to everyone. And next, we're going to look at, when we're talking about decentralization in Bitcoin, some of the things that we need to discuss is who maintains the record of transactions, the record of blocks, who maintains them, who has authority over which transactions are valid, who can decide which transactions are valid, who creates new Bitcoins, and who determines the rules and the value. How do they acquire their value? And these questions are not only limited to Bitcoin transactions. Even when we're making Bitcoin wallet, or we're having Bitcoin exchanges, or for Bitcoin service providers, all of these need to understand the underlying technology behind Bitcoin, where the transactions are coming from, who is making the coins, how those coins are going, who has authority for what purpose. All these concepts are not only related to Bitcoin, but in blockchain technology in total. So if I want to make a wallet, if I should know who can make the wallet and what authority I have over my wallet, if I want to make a transaction, what authority with what authority can I send Bitcoins? And the next, what we need to understand is that Bitcoin is a peer-to-peer network, and we're going to look at mining and look at updates of software. So first, peer since Bitcoin is a peer-to-peer network, this means that anybody can join the Bitcoin network. Anybody can come today and download the Bitcoin client and be part of the network. So there's no barrier against who can come in. You cannot come in, this person cannot. Anybody can download Bitcoin client and come into it. However, mining is open to anyone, but there is a concentration of power. Anybody can come and create mine bitcoins and creating of bitcoins. This is not restricted to anybody. But to complete that mining process, you need to possess that computational power in your system or in your miners or in your mining setup. So inevitably, only a certain amount of people can do that mining, and the rest of the people have to adjust on the network. So though it's open, it's still concentrated. And finally, updates. Who can make updates to the whole Bitcoin network? That means the Bitcoin blockchain technology. Who can make updates? The developers. But who are these developers? Developers are part of the community. So these are people in the community who other people trust. Okay, he has the knowledge, he has the skills. I trust him to make changes. So they make changes, they roll out updates, and everybody accepts and updates their software as per when updates are received. The next concept that we'll be looking at is about consensus, and in particularly distributed consensus. So the key challenge of having Bitcoin and blockchain, the key technical challenge is having, if if it's decentralized and there's no centralized authority, how do you make sure that uh, all all the people are agreed on the same value? Like for example, if uh, if two people have a bank account and there's a bank which decides how much money which maintains how much money is in each account. If you remove the bank and have only two people with bank accounts, how are you going to maintain how much money is in whose bank account? One might say he has more, other might say he has more than he has. So if there's no central authority, how can you maintain some consensus among everybody? So this is one of the key challenges. Or in other words, we can say, how do we decentralize Scrooge coin? Now in Scrooge coin, we had one Scrooge, one central authority, and if we wanted to get a transaction from A to B, each transaction had to be signed by Scrooge. If a transaction went from A to B and without Scrooge's signature, it is not considered as a valid transaction. So basically, the idea behind distributed consensus is how can we remove Scrooge? How can we remove the central authority and have transactions validated amongst between two pairs? And here we see why we see the motivation behind consensus. It's all for bringing about reliability, that people can rely upon the system, that its system is trustworthy and fault tolerant. And another motivation of solving consensus problems is to have distributed key value stores. So when we're storing keys and values, if we can figure out how to store keys and values, this will enable us to, for a lot of applications outside of blockchain, including how do we store DNS, domain name service, how do we store URL and the IP address, public key directory, and stock trades. How we if we can find out how to make a proper consensus protocol, it can solve a lot of problems for us. And this has actually have this has also been the target for many alternate altcoins, like Ethereum, Dogecoin. These coins, what they are trying to do is solve these problems. These Maybe they'll just put some modification to Bitcoin, but they'll be able to solve some problem like this or add some new feature. This is why altcoins. But this is the idea behind motivation of consensus algorithm. And so now let's move and like to define distributed consensus and how it works. So we can see, if something is consensus, it means that once the protocol terminates, all the correct nodes decide on the same value. Now there are two concepts here. One is the same value and one is the correct nodes. Same value means if I have two nodes here and I have a variable var and it's 13, then both these nodes agree that the value in that variable is 13, right? And the second concept here is correct nodes. So if I have another node and it's a faulty node or it's a malicious node, some hacker is there, and it says that no, this is 12, it says it disagrees with that, and then oops, and it disagrees with that the value of this variable. Because this is faulty, we don't need to include it in the equation. All we need to include are the correct nodes. So distributed consensus works only for, we consider only correct nodes, and the value that was proposed by the variable needs to be proposed by some correct. So whatever the faulty node says, whatever it proposes, whatever it says is the value, we should not consider it. Consensus protocol should only consider those which are correct, valid nodes that are not malicious. They are not. We know they are honest. We know this is what we're trying to develop for consensus algorithm. So now let's take an example. In this, let's say there are two people on the Bitcoin network, Navya and Vivek. And so Navya wants to send a transaction to Vivek. She wants to pay. She wants to pay. Let's say Vivek is some song, a singer, and he has some music album, and Navya wants to purchase that song and buy a copy. So how does it work in Bitcoin? First, she has to broadcast the transaction to all Bitcoin nodes. So Vivek is somewhere on this blockchain network, and what is done is we have this transaction. The transaction is signed by Navya, so everybody knows it's coming from Navya, and it's going to the address of Vivek. So it's signed with his public key, so only he'll be able to get it. So this is a transaction. It has everybody knows where it's coming from. That means everybody knows it's authentic, and it goes only to Vivek. That everybody knows it's confidential. And this transaction is broadcast. So all the nodes on this network will all the nodes on this network will get this transaction. And some important thing to note here is that Vivek's computer is not in the picture. Like, we're not talking about Vivek's computer. Whatever Vivek's computer does, all Navya needs to do to pay is to broadcast this transaction. There is nothing to do. Vivek's transaction does not need to accept this transaction. Vivek's computer does not need to be online. Also, all that is required is for the person who is paying to broadcast that transaction to all the nodes in the network. And so what the idea behind how we can, since all the transactions are going to all the nodes, we can now develop an idea about how consensus can work. And there's two main ideas here. The first is outstanding transactions, and the second is block of transactions. So let's say we have a node. Let's say we have another node which is run by Kavya, and there's say Ashok. Two more nodes in the network. They both have a sequence of blocks that have sequence of blocks. Yes, they have a sequence of blocks of transactions that have reached a consensus. That means we have Kavya has this sequence of blocks, and Ashok also has the sequence of blocks. And these sequence of blocks are same because they have reached a consensus on those. And apart from that, they have something called outstanding transactions list. Outstanding transactions. And here is where the transaction from Navya to Vivek comes. Maybe let's say Ashok has maybe heard some other transactions. Let's say it heard some Vivek to Kavya or some other transaction. So each node has its own, what it's heard, it puts as an outstanding transactions list, and what's they have confirmed, its consensus, is in the sequence of blocks. So you can see that each node will have a different set of outstanding transactions list, and but that we will see how we can. So what the consensus is on the block of transactions. So the aim here is to decide on getting your transaction from your outstanding transaction list to the block, and the block to the blockchain. So let's consider there are now 3 blocks on the blockchain. This is everyone has agreed to these 3 blocks on the blockchain, and we have three nodes, and each of them have their own blocks. Now these transactions that are inside the block came from the outstanding transaction lists of each of them. Now the consensus protocol works amongst these people. It works between these people. They have to decide on the consensus protocol. So what we need is that it's okay to select any valid block if proposed by only one node. So any one of these blocks can, each of these blocks have equal chance to be proposed to be added to the blockchain. So let's suppose that one block has been selected and it has been put in the blockchain. Now they have reached a consensus for these 4 blocks, that these 4 blocks is the blockchain. Next, one of the other nodes can propose a block, and that block can be added to the blockchain. Why consensus is hard? What is so difficult about this idea? Seems simple, but these nodes are not people, they are computers. And so nodes may crash, nodes may be malicious, the people who are using them may be wanting to cheat the system. And the network, and there's also problems with the network. For example, all pairs of nodes are not connected. We saw in the network diagram that every node is not connected to every other node in that. Some are connected, every node is connected some way, but not directly. And false in network. They may be false in network. Because this network is completely digital, they may not be, there may be 2 pairs of nodes that are not connected because of some fault or something. And also latency. Latency is also a big problem because the transaction that was happening from Navya to Vivek may be received by Ashok at one time and may be received by Arun at some other time. So, and by that time maybe Arun got some other transaction. So which happened first? And this is a problem because there is no notion of global time. So there's, if there was a notion of global time, we would say, okay, if you have 0 and 2, and one transaction came here and another transaction came here, okay, take this transaction as the first and this transaction as the second. But there's no notion of global time. So what may be first for you will not be first for somebody else. So how do we maintain the consensus value? And this is important if you're having a value like a coin which is changed by different transactions. So you need to find out which transaction came first, which transaction came second. Based on that, the values will change. And theory does not support many of these things. We have something called the impossibility results. These are theories that have been proved theoretically to show how difficult this problem of consensus is. One example of this is the Byzantine generals problem. Let's look at this. So suppose we have a suppose we have a city, and this is a city with walls, and there is an army A, army B, army C, and each army has a general who is leading that army, and they need to attack this city. And between the two armies, they can communicate using messengers. So they have messengers. Now what could happen? Let's say A wants to attack, let's say A wants to attack the city. So what A will do is A will send, let's say A wants to attack, and it will send a message to to B saying attack. It'll send a message to C also saying attack, and so they'll all be able to attack and the city. But what if A does not want to attack? So it sends B also an attack. But let's say A and C do not like each other. A does not like the General C, and it tells A to attack. So what will happen? C will go and attack, and since it's not received support of A and B, it will fail. They'll die. So the problem here is how can you attack a city when all the honest generals will have a consensus that, because there may be some generals who are going to lie, there may be some generals who are malicious, then they may collude amongst themselves. At least the people who are not lying, the people who are honest, can we find a way to gain consensus among them? So the Byzantine general's problem says that if one third, if greater than one third of the nodes are honest, then we can, there is possible to get some sort of consensus. So for example, in this case, if 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 two nodes are honest, let's say uh, A and C are honest, then this will not, A will attack and A will attack, and let's say B receives attack but still it retreats, no problem, because majority, there are more nodes that are honest and that will attack and gain victory. So if more than one third of the nodes are honest, then we can achieve consensus. The second impossibility result is the Fisher-Lynch-Patterson. There are three scientists, and they tried to solve a problem that was uh, troubling the computer science world for very long. That is it possible to get a consensus algorithm for asynchronous distributed system? So for synchronous, we know it's possible. You can have a time, you can say, okay, this came first, this came second, we can achieve consensus. But for an asynchronous, can we do it without? And this Fisher Lynch Patterson or the shadows, no. They proved mathematically that you cannot get consensus in an asynchronous distributed system. If on the condition of that consensus is impossible with the single faulty node. If even one node amongst the nodes in the asynchronous system, even one is faulty, consensus will not be possible. And this is proof that it's impossible. And we know most practical distributed systems, it's possible that some node can be faulty. It's possible that some node will crash. So how? So then, if it's not possible, how are we going to do this consensus? And but effort, we'll see how we can still apply. We can still get consensus to Bitcoin in spite of all these theory. Before, and we also looked at let's also look at some protocols that have been defined. One is the Paxos protocol. So let's look at that. So Paxos protocol says that there are two types of things. There are proposers and their listeners. Two as proposers and there's acceptors. So let's say we have a group of people A, B, C, D, E, and then we need to decide what is the value in some variable. A says the value is 13. B also says, yeah, it's 13. C says it's 12. D says it's 12. E also agrees it's 12. So who are the first people to say, to propose a new value? A was there and C was. So proposers, you have A and C. And who are the acceptors? Acceptors. The acceptors are people who, after something is being proposed, they accept it. So that's B, E, and D. The job of the acceptors is to find out what is the maximum, what has the majority of other acceptors decided. So we can see here that the majority E and D have agreed on 12, And so 12 is the answer that is chosen. So as you can see, this is always produce a it'll always produce a consistent, it'll never produce inconsistent, always be consistent. Why? Because we always see what the majority is saying, but sometimes it can get stuck. If some node is down, okay, now which one do you do? Now which, if let's say D is down, now which value is it? Is it 13? Is it 12? So there are some problems. That's something called access. And what these results, what these concepts tell us is that more about the model than about the problem, because all these, they tell us it's all based on how the distributed system is built. It's based on how the nodes are set up, how the what is the architecture of this network, and it says less about the problem of consensus. And this is leading us to why we can still implement consensus in Bitcoin. Models were developed to study systems like distributed databases, where you have transactions and you have concurrency control, so that we can get the correct value of the variable in a account or in a database in this thing. And Bitcoin worked, though theory said that it would be difficult to make consensus. uh, Bitcoin works in practice. It works. Bitcoin is able to put consensus, and theory in fact is actually catching up. Theory is still behind how Bitcoin is practical thing. Does that mean that theory is not important? No, theory is important, because using theory we can there may be other attacks, there may be other things that possible loopholes in the Bitcoin structure, and to find out these and to predict these unforeseen attacks, we need theory. And now, what is different with Bitcoin? One, two major things that are important is incentives and randomness. This is not there in your usual distributed system. What are incentives? Incentives are rewards that you give to somebody that that encourages him to be honest. In a normal distributed system, you cannot. Let's say you have microprocessors and they are connected to a CPU. You cannot reward a microprocessor for doing something honest, or you cannot reward something for not being faulty. But in Bitcoin, you can, because Bitcoin is a currency. It's money. So somebody who has been honest, you can actually give him Bitcoin. He can be rewarded monetarily because it's a money. You can buy something, and you can, it has value. And second thing is randomness. Randomness in the sense there's no endpoints, and instead there's long time scales. What that means is, for example, if you had a ring of in the ring based in the ring or whichever distributed system, we can we can we can get consensus by, let's say, the first says something, second whether it agrees to that, and the other whether it agrees to that. We can do consensus based on that. But in Bitcoin, there is no first node, there is no last node. It's a network. So the consensus is spread across the network, and there's no way of telling, okay, it started, okay, here it's ended. And instead, what happens is the consensus will spread over the network over a very long time as nodes begin to accept blocks, reject, and practically this takes like 1 hour in the Bitcoin that we have now to get a good probability that you will that the block is valid. It'll probably take 1 hour, and we'll see more about this probability. And consensus, and something that's unique to the blockchain is that there is no identity. We'll look at this now. Why are we talking about identity now? If you see algorithms such as bully algorithm or any other algorithm, like, we have nodes that have identities. Let's say this priority 1, 2, 3, 4, and if something goes down, then coordinator is selected as the top. This all works when we have nodes which have any identity. But instead of this, 1, 2, 3, if they were X, Y, and Z, and U, and if one goes down. Now, which one do you put? So nodes need some idea, some sort of way to identify themselves. And Bitcoin, it lacks this kind of identity. And for security, we need to assume that less than 50% are malicious. This is just more like a moral assumption that not that the network is not overrun with hackers. That at least less than that at least more than half are honest people. And now we have the question: why doesn't Bitcoin have identities? Why don't they give, like, for example, in if I want to send somebody Bitcoin, why is my identity not on the blockchain? And actually, identity is hard in a peer-to-peer system because there's no, if you're having a college and you're having two people in that college, you have identities. They have two students. You have identity cards for both those students, so you know who those two students are. And who issues that identity card? The central authority, the university office. So, but if there was no university office, you would not be able to verify which student is who and what is the identity of those students. And this causes something called Sybil attack, whereas where a single person, say A, he creates multiple nodes, and these multiple nodes are run by the same person, because we have no way of telling who this node belongs to. We do not know this identity. This identity remains a mystery. And and also, this is something how Bitcoin was built on. It is built on pseudonymity. So where you don't need to know who this person is. It's not required for these transactions, for these nodes to know, to transact from one to another. You don't need to know who is there. What you need to know is the address of this node. That's what's important. Only the nodes are required. And even if we found a way to put identity of people in nodes, it may not be implemented in Bitcoin because there's no need to do it. And it's not it would be against the Bitcoin policy and for what they made it. And instead of starting from one start point, which there is no start point, we're going to try and select a random node. But then, how do we select a random node if we don't know the people? A way we could do this is using a raffle. Now, in lotteries, how in lotteries, what happens in lotteries is you buy a ticket, and the ticket is put in the lottery, and one of those tickets is selected. It's not necessary to know who the person is who wrote that lottery. All that is necessary is there's a lottery number, and that lottery number will be assigned to some person, will be bought by some person, and that number is all. The number is what wins the lottery, not the person. So in the same way, even so, when tracking or verifying identities is hard, we give people tokens or tickets. So same way in the node, that's the way. There's a pseudonymity. We don't know the person, but we know the node. And then it is possible to select a node, to select one random node. So let's say we select one random node. Second concept that we need to know is implicit consensus. That means instead of one node coming and saying, I reject this block, I accept this block, something something which is in the behavior of the node should tell us what it has decided. So let's say a random node is picked, and the node proposes that, okay, this is the block, this is my transactions, I put in a block, and I want to put it in the blockchain. If a node extends it, that means if a node has a blockchain like this, and there's a new block that comes, and the node puts it back in this, that means it has accepted. Implicitly, the meaning is it has accepted. So when it proposes a new block, that block will have a hash pointer to this. So the implicit meaning is that the node has accepted that block. If it ignores, that means if this the new block that has been proposed is actually pointing to this, what that means is that it ignored the middle block. It's not taking the it ignored that. That means it rejected that block. That means it's not using it in its blockchain. And so this is only possible because block contains hash of the block it extends. If there was no hash, then we would not be able to know whether a block, this implicit consensus would not work. We will not be able to know whether a block is taken or is accepted or rejected. And that brings us to the consensus algorithm. Now the consensus algorithm, we see this is the way it goes. So you have a new transaction is broadcast to all the nodes, and each node collects the new transactions and put it on block. So it heard of the transactions, it took the transactions and put it in the block. Each round, a random node gets to broadcast its block. So one of those nodes will take the block and will send to the other nodes saying, hey, this is my block and I want to put it on the blockchain. Other nodes accept the block only if all transactions in it are valid. It means unspent and they are valid signatures. Other nodes will have to verify. We'll see for example, if it's a node signed by Vivek, they should know that Vivek's when they put Vivek's public key, it should match and should be authentically matched to him. So if they're able to do that and all the transactions are valid, then only they'll accept the block. And nodes accept their acceptances of the block by including its hash in the next block we create. So the next block that is proposed will include the hash pointer to that block which was proposed earlier. That's the way that block will know that yes, that block is accepted by everyone. And now, what is there any problem with this? What could a malicious node try to do? So here we have a blockchain which has two blocks, and here we have, let's say we have two people again, Navya and Vivek, and Navya wants to pay Vivek, and uh, this is a transaction just signed by her and paid to Vivek, and so this is a block and which is pointing to the block that came before it, and this block has a hash pointer that 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 points to where those coins came from. The CN is this coins of Navia, and the hash pointer points to where those coins came. Maybe those coins, maybe it was created, or whatever it was, where those coins came from. This pointer. So this is a valid transaction. It's a valid block. But let's say there's another. Navia sends another transaction where it says coins of Navia to go to Navia to N prime. So N prime, let's say, is another node that she only um, that Navia only controls. This is again signed by Navia but paid to Navia, and it has a hash pointer, and that will relate to the one that to the block that where it was. Now the problem is the nodes don't have any idea which is true. We may know that Vivek is a singer and Navya wants to buy a song from Vivek and Vivek wants to let her download it, but the computers don't know this. They don't know which transaction is true and which one is false. So here it's as likely, the first one is as likely to be accepted as the second one. Let us assume the second one is accepted. Let's assume that the malicious code has worked and the scheme has worked and the second one is accepted. This is an example of something called double spending. Double spending is where it's sent to one person, but it's sent back to the same person, the same coin. And if that is accepted, then the new blocks which come, they all get added on to this. So now what has happened? The blockchain has come like this, gone like this, and like this. And what happened to this? This became allowed. Something we call an orphan block. Because now it's completely out of the transaction. So let's say what had happened was Vivek saw the coins he was getting. He heard that now he is sending me coins and allowed her to download the music. Then the second transaction came and that became accepted. And Navya got her coins back. But Vivek has already given the music. So Vivek lost his music and Navya didn't spend anything. So she effectively got that for free. This is a problem. And what will happen is that that thing will go. So this is a problem. We cannot allow this to happen in Bitcoin. But does this happen in Bitcoin? Is this how it works? So let's look at it from Vivek's point of view. There are two blocks on the blockchain, and first he hears about the transaction. He hears that coins are being sent. He hears. Now, when as soon as he hears, he can give the music. He has the chance to do that. But but he can wait for that transaction to come into a block. And once the block has come and that block has linked, he can then give the music. So he can give it over here. That's a zero confirmation transaction. He can also give it after the block has come. So that's a one confirmation. But then again, we saw there's a possibility that another transaction pointing back to Navya is going to happen. And if that happens, then Vivek is going to lose his music. So what he can do is he can wait. Let's say this was accepted and another block came in. So once the second block comes, now he has some more confirmation. Okay, this block is part of the blockchain. That Navya has not tried any double spending attack, and the block which he had sent to me, the transaction which I saw on the block, it's actually going to be part of the blockchain. He can wait for even more confirmation when he sees the second, if he sees this second block, and then he can decide. That will be called a third. It's a third commercial. So you 1, 2, and it's third. So now he is more sure that there's no double spend transaction that has been accepted into the blockchain. And the transaction which I saw, that is the one that has been part of the blockchain. And what we see is double spend probability decreases exponentially with number of confirmations. As the confirmations increases, the probability that you'll be affected by a double spend attempt decreases exponentially. And so what happens today is 6 confirmations are the standard. So today in Bitcoin, if you want something done, the merchant will usually wait for 6 confirmations. That means 6 blocks will join on the blockchain, 5 after the one containing the transaction if you paying that person. So this eliminates this rapidly reduces the probability of having double spend, because if something is part of the blockchain, it won't be right. There's less probability of something of another block coming here, because we already have this blockchain. So what what uh, what honest blocks do, let's say even if a block has come here, but this is the longer block, and and honest nodes will always choose the block that is long. So the even so, as let's say if 6 heuristic, 6 confirmations, we have 6 more blocks, and this is a much longer valid block, and so the probability that this is accepted is gone much higher. So as the number of blocks increases, the probability that double spend attack rapidly decreases, and we can see this. So as the thing gets, so because valid is always what's longest. This is the idea. Valid is always the longest, and so as we get more, we know it's going to be the longest. That there's less chance that the spending attack block can have more blocks. So let's recap. Protection against invalid transaction is cryptography. When a transaction is mentioned as valid or invalid based on public key and private key, and these are purely mathematical. They're purely cryptographic. But this is enforced by consensus. This is enforced by consensus. Based on the private keys and public keys, all the nodes can know whether this is authentic, whether this is confidential. Whether, and then they'll decide that that transaction is valid. But protection against double spending is purely by consensus. That means to prevent double spending, we're not using any cryptography. We're not using any keys. We're purely We really have a consensus protocol, and we're using only that protocol to prevent double spending. And the concept that of probability. Here we're not saying yes, this block is valid, this block is invalid. We're only saying the probability that this block is valid or invalid. So you're never 100% sure a transaction is in consensus branch. Guarantee is probabilistic. So this here you see how that theory does not, those theories do not work, because in there value is 13 or 12. It's either 13 or it's either 12. There was no probability thing. But here, since we're using probabilities, since we have incentives, since we have randomness, those theories do not apply. The impossibility results, and therefore in a blockchain we are able to get consensus even though it's an asynchronous system. So this was how decentralization implemented in blockchain, how consensus algorithm works, and how double spending attacks are prevented. Thank you.